So good afternoon, everyone. Again, I'm taking the last session of this workshop, which is a TDCF. It's also a little bit different thing from WIS, but TDCF is one of the parts QMD has asked us to do. So I would like to cover a little bit complex system of TDCF. So time-wise, my presentation slides are actually there are a lot, but I'll pick up some important parts, and then I'll leave the presentation so that you can review after this lecture. Let me have a seat. This is a tutorial session, so it's a little bit long, but please follow me, and please ask questions anytime if you have difficulty in understanding. So the scope of this tutorial is a basic of buffers. The reason I chose buffer as an example is this is kind of typical and relatively easy to understand compared to grid, for example. And Cerex, as I said before, has basically structurally the same as buffer. So you can, if once you understand buffer, then you will be able to understand Cerex in the same way. So this is basically our tutorial about buffer. So, yep. Yes, buffer and Cerex share grammar, kind of, the rules. But buffer is a binary, and Cerex is a characters. Yeah, that's basically the same rules. So buffer is a binary code. So if you open one buffer file, then you like 0 and 1s, all this. So in other words, just a privately random string of zeros and ones. It's a binary code. So this is a slide I used in the second day session, and the structure of buffer product is like this. So it has section 0 to 5. So what I'm now talking is how this is represented in buffer in an example. This is the same, but the sections of the buffer message has a 0 to 5. So 0 is indicator section, 1 is identification section, 2 optional local use section. So section 2 is sometimes not used, so it's optional section. And the third is section 3 is data description section, 4 is data section, so the actual data is in section 4. And 5 is end of message. So section 0 is indicator section. So this section contains the character string buffer. So you can know if you have the ASCII. Sorry, this is actually encoding in ASCII way. So buffer, you find a buffer and you would know this is a buffer file. And the next thing is the total length of the message. And the third one is the buffer edition number. So I don't have a explanation of edition, but yes, there are some editions of buffer. And actually in November 2012, that's the last November, buffers edition 3, we basically ended using buffer edition 3. So now official version is buffer edition 4. So if you start using buffer, it's good to use edition 4. But the existing buffer 3 edition products are still floating, so you might need decode buffer 3 edition as well. But if you create buffer yourself, please use buffer 4, not 3. So the section 0 is length, it's always 8. So octet 1 to 4 is buffer in kind of in a character format, and then octet 5 to 7 is total length of message, and octet 8 is edition number, currently 4. Yeah, but 3 is still used. That's what I said before. Octet is a set of 8 bits. Like byte, but eight bits. Always 8 bits. 1 octet is always 8 bits.
The electronics machine or the electronic language of the machine itself. It's switch on or off. Each octet switch on or off.
On or off.
So 0 is off, 1 is on, and with the 8 octet you can define any character on the keyboard of the computer.
Ah, yes. Thank you. So octet, 1 octet consists of 8 bits. So now we have the length of section 0 is always 8 octets. So we are trying to decode the random strings of 1 and 0s, and the first 8 octets are section 0. So octet 1 to 8 is the section 0. As I said before, it's always starting with buffer. So 1, 2, 3, 4 is a ASCII of buffer. And length of the message, and the 8th one is the edition number. In this case, it's 4. Yes. The next section is identification section, and the section 1 contains the table versions referred to by this message, and an overall description of the message contents, including the originating center and subcenter, the data category and subcategory, representative date and time. Yes. So the section 1 is all about what is this data and who created this data, kind of stuff, and the typical time. In observation, for example, in observations case, probably the reference time of the observation of the message. And section 1 is length is at least 18 octets, and length of the section, the table, master table version number. Sorry, this is a master table. So in WMOs, if you are using WMOs table, then that will be 0. Another table exists actually in IOC, and in this case, this number becomes 10, but probably it's a very rare case. So usually it is octet 4 is 0. And in the octet 5 to 6, this represents originating center, originating subcenter and center. So each center has its own code table figure, and by reading this part, we can know who created this data or who is responsible for this message. Octet 7 is update sequence number, so probably it's easier to imagine that sign-up has sometimes delayed data. In this case, these ones, or correction of data, in these cases, this update sequence number is counted up one by one. So if you don't have, if you have numbers in octet 7, not 0, then you know there were original data before that message. Flag. Yes, the octet 8 is a flag if there is an optional section or not. And octet 9 to 10 is a data category and subcategory. So from this part, we can know what kind of data this is. So SINOP or temp or satellite or oceanography or everything. This is also referred to another code figure table, code tables. And octet 11 to 12, this is a master and local table version number. So as I said before, the TDCF is defined all by the tables, and each time someone adds new entries, table versions are counted up. So now BUFR table is, I think, version 19, but 19 includes all of the descriptors defined right now, but some centers can use older versions of table. So if you, when you decode TDCF, you need to know which version of table was used when this message was encoded. So that's, in this case, octet 11, octet 11 to 12 is the location to read. That's the master and local table version numbers. And the next part is a time, date and time. So if there is a, if this is a sign-up of today's 00 UTC, then the date and time is represented here. And octet 18 and 18 and after is reserved for local use. So if in many cases this is not used. So from what I said, getting back to the first example. So from here to here, now in this case, the length of the section 1 is 18 octets. So from here to here, the buffer represents master table or addition number and buffer table numbers and date and time and stuff that I explained in the last slide. So section 2 is actually optional, and sometimes, sometimes an automated data processing use some of the section 2 optional information. So the typical example is database keys to aid searching for specific data without decoding the message or anything else a processing center may find useful. Yes. So in many cases, this section is not used. So section 3 is kind of core of the TDCF, and this section contains a count of number of data subsets. Subsets means if sign-up includes 10 observation stations data, the subset will be 10. So section 3 includes the number of data subsets first. And also section 3 has a flag indicating whether or not the data are compressed or not, and observed or forecast. So there is one octet representing compressed, uncompressed, or observed information or forecast information. It's a little bit complicated, but you know. And the list of the data elements that are contained in each table, each data subset. So now we are in the section 3, which is data description section. So this is basically the list of descriptors. So section 3 details, I'm a bit repeating, but length of section, octet 4 is reserved and always set to 0. And 5 to 6, number of subsets. Octet 7 is flag. This is observe forecast, observation or forecast, and compressed or uncompressed. And octet 8 and after is a list of descriptors. So as I showed now, each descriptor concludes 2 bits S and 6 bits X and 8 bits Y. Sorry, I'm explaining this later. So this is a list of descriptor. Sorry. So now we have a very short example. So there are only small number of, it's only 7 list of descriptors, but section 3 is from here to here. And main part of the section 3 is a list of descriptors that represent what kind of data is included in section 4, which is data section. So the section 4 is our actual data. So first, yes, so this section includes real data as specified by section 3. So sometimes data are compressed and uncompressed, which is represented by the flag in section 3. So as always, the section starts with length of the section, and octet 4 is set to 0, and octet 5 and after is a binary data as specified by section 3. So once you know the template, then you'll start reading real data from section 4 of the octet 5 of section 4. This is the real data part. So this is a small example. So there's only 8 octets in the section 4, but after the description section followed by the real data section 4. We are now reaching the end, and the section 5 is the end section, and section contains a character string 7777. So basically, buffer starts with the 4 letters of BUFR buffer and ends with 7 characters of 7777. So basically, most of the decoder read between buffer and 7777. So this is kind of a unit of one buffer message. So after the data section, section 4, following the section 5 is 7777. So now we decoded all this, this one example buffer message with section 0 to section 5. Yes. This is a kind of basic buffer structure. Is everybody with me? Have any questions? Yes, yes.
It's easy for the human to interrupt the message or to understand what is going on. But with such a short maybe 6 or 5 frames, it's impossible to encode or to decode the messages. Am I right?
Yes.
I think what he's asking is error correction. So if it's ASCII, you see that it's wrong. But if it's binary, then who tells you that it has been garbled? You know, if there's a transmission error, how can you detect it?
Well, sometimes, yeah, maybe I didn't. 77, yeah, this is one of the things. So if you don't have.
It's just the first, then the decoder program will not be able to find the list. So he will not know this is a buffer message.
Yes, yes, that's the problem. Yes, buffer.
It's more like to transfer anything or something.
No, you can't transfer anything between fields in this case.
But almost use the buffer, almost use the buffer, almost to transfer something.
Yes. So this is will lead us to another area, which is we should also pay attention to the which protocols of data transfer we should use. We should use a high secure protocols.
Yes, yes. It's basically designed for GTS, so that's probably explains part of it. Yes.
Also, I asked you earlier, if you still remember, about why we go to this kind of program, and you told me something about compression and memory and data
Yes.
store, something like that.
Finally, yeah, can be very compressed. Yes, that's one rationale. But yeah, sometimes difficulty in understanding. That's true. Yes.
It's my feel, what I got from the from lectures about it, that I am sure I am wrong, but I need some feedback from you to correct my what I did. That if you include some reservation in physical tools, let's say temp reservation,
Yep.
it will be shorter in space, in computer space than in binary.
Yes,
But
that's
if you
yeah.
were, I think if you go to increase the instruction, the gap between the binary and the space will become closer. At some point, they will become equal, and then the binary will start to be less in the
Yes, yes.
memory.
Yeah, in many cases, in a very simple the traditional code is actually smaller than buffer template. One is sign-off's buffer template is very complex, including other instrument information and stuff. And actually, this is all filled with missing sometimes. But in a well,
But frankly, it doesn't matter. Uh, we are where computing power, the processors in your computers, it doubles every 2 years or so. The transmission time tenfold every 2 years. So there is no point in using 50-year-old code that were designed to uh, turn every bit around because we only have telex machines. Nowadays we have fast lines, so we can make our lives easier. It's not so much about counting bytes nowadays, it's about managing the information we have and quality control and all these other things, flexibility, how to manage several versions of the same code at the same time, etc., etc. So that's the thing. Your observation is very right. Yes, um, the path can be shorter, but it doesn't matter. Not at all.
sometimes yes.
It's not acceptable to say traditional food.
What?
To say a traditional food, that's not acceptable. Because it is until now, is using food, for example.
Yeah.
The buffer for the steaks or other things, it's just buffer for them.
WMO's official position is eliminating tag and migrate all tag code forms into buffer. But
Why you use all now?
why use old what?
All.
Old one?
It look old. I use it, it look old. Okay?
Yeah. Personally, I think TDCF can be used for things tag can't represent. But that's sorry, WMO's formal position now is eliminating all those old ones and integrate the data processing only into TDCF. Yes. Good. Go. Okay, maybe go. Yes.
The main reason to use this kind of change the text data to buffer for
Yes.
transmission means like when I receive this message by MSS,
Yeah.
I can read it as text
Yes. The buffer.
buffer. You mean you compress the silence,
Yes.
100 silence, and you send it to me,
Yeah. In a one buffer message. Yeah.
and I send you my transcript.
Yes.
Then I transfer this to the patient communication system.
Yeah.
You can read this data as text data.
As text
I mean,
means.
you can read the data as text, or you can modify the data.
After the call, WIS call, deliverable call, I
After.
can read it.
Yeah.
The main question is, there is wrong with the original message. I didn't receive a message as a signature. It's impossible to read. This is the first question of mine.
Well, if you have table, yes, you can.
Yes, I have to.
Yeah. Then you can decode, right? Sorry, I don't understand the question.
Okay, now we can like let us make for instance, you send it now
Uh-huh. This
100
for
sites, etc.
Yeah.
Okay. Can you tell me when I receive this message on my messaging switching system?
Yeah.
Messages.
Yeah.
The operator who will see the message as images or as chart or he will see as text data. It's 100 silence.
Well, data itself is a binary, so like this. So you.
No, no, no.
Yeah.
I think what I understand the question to be is, say, the traditional approach. When it comes out of the system, it is a file, and I open it in my editor,
Yeah.
and then I see what's inside. Whereas TDCF, I open it and it's zeros and ones, and it looks, I don't see it. So he would like also, to click on it, and then the right thing opens and he can see it. But what images? So now,
Well,
how does it work?
in many cases in GTS, you could know from header because buffer headings start with I, so yeah, you can most of the time you can trust the I headers will be buffer. Yes, but
About the quantity. Quantity of the message.
quantity of the message means how do you know? Right now? Or?
So, for example, in case that buffer decoding program I saw,
Yes,
right?
yes.
So maybe I click on the buffer message, then the buffer decoder works, and then Notepad open and show me the sign-offs, or maybe if it's an image, can the paint go up and I see the image, or how does it work?
Because now you can see it as an image. The buffer will you can display the buffer as an image.
So in many cases, message switching system has a buffer decoder, and yeah, first decode and store in some kind of database from where some forecast or imaging server read the data. Yes.
I was working 8 times with buffer and data. When they receive it from that memory. No, from receive that.
I was not, I'm anyway not an expert. But I think here the question is how to deal with buffer messages one receives.
But I can say from my, let's say, mathematics knowledge, if you lose any bits of the binary message, you cannot do anything with the message.
Yeah, I sometimes validating the buffer message, some original encoder makes, and then I open this binary file by binary editor, and I look for some known strings, and then sometimes 1 or 2 bits missing, then I put it 0 or something, and I can read by buffer decoder or something. Yes. So it can happen, but it can be a very manual.
Yeah, but to be fair, this can also happen with the task. If the message is garbled at the wrong point, then you have just lost the information.
Sometimes you can do something, and we do it in the ground as I told you. Sometimes I receive a signal, and then my a logic error or a scientific error, and I can correct it.
Yeah, you can do the same also in buffer, but sometimes even in silent you cannot, because when the observation itself is garbled, then it's just wrong or not there. So the same also applies to this, but I think reasonably the classification layer should make sure that nothing is garbled. So that's it very good. Now, gentlemen, should we continue? And ladies.
We were just speaking about this conflict, because here we were speaking a lot about the type of the messages and why it is necessary. We were speaking that maybe WMO should speak more about the quality control, right? And it has the services when they migrate to the buffer also introduce methods for quality control, and if there are these flags, who is doing what? This is what we were speaking. I'm sorry for this subject, but we were speaking about meaning what was the benefit of benefit. You mentioned it, but I just said that there is no coordination about the benefit of buffer in terms of real-time quality control. This is my experience from you.
And you know this from basic version.
The benefit of quality control.
Yeah, because this is the benefit of buffer. To really say to your partners, to whoever you're sending, yes, I make a quality control check, and even, I don't know if we did in some new buffers something about what type of quality control. This is, I don't know. I was not working with the buffers for many years.
Quality control buffer format, you mean?
How many flags you have for quality control?
Well, it depends on template.
Depends on template.
Yeah.
You could describe somewhere what type of quality control you start with.
Yes, of course. You can include some kind of quality control of instruments and observation and everything in buffer template based on depending on which data you are talking about.
So I think this is the most benefit, that you could claim, okay, my equipment has this qualities and my data has that quality.
Yes.
So quality control, yes, so very important.
Almost middle. Yeah. I can go a little bit more.
So yeah, then let's continue this intermediary discussion.
Probably you need to understand what is buffer descriptors. So that's the next section. So section 3 as I said before, contains a list of buffer descriptors. These describe the data elements that are contained in section 4, that is data section. The most descriptors are references to buffer table B, C, and D. Using the list of descriptors in section 3 together with the tables, these ones, it is possible to unpack the data in section 4. This is the buffer's basic, okay? So there are several types of buffer descriptors. Element descriptors is the most important ones defined in table B. And replication descriptors, this is used for make some replication in the data, because in many cases one data have a lot of the same replication. The another one is operator descriptors. This is defined in table C. And sequence descriptors, which are defined in table D. I think first thing everyone needs to understand is what is element descriptor and sequence descriptor. Probably from these two, you would understand most of the buffer template. So the buffer descriptors are specified by 3 numbers in 16 bits, which is 2 octets. And it's represented by f, x, y, and f is 2 bits, x is 6 bits, and y is 8 bits. So you'll see the example later. So the first one is element descriptors. This is the most important ones, defined by entries in table B. And element descriptors always have f with 0. So something 1 digit, 2 digit, and 3 digits. So table B descriptors are always using starting with 0, and some number with 2 digits and 3 digits number. So each element descriptor describes an encoded value, such as the value of a meteorological parameter, such as mean sea level pressure, temperature, and wind speed. And also can be instrument details, can be location or date and time information, can be quality control information, as Diana said. So corresponding to the types of descriptors, buffer tables, there are 5 tables involved in buffer. So these are called table A, B, C, D, and code and flag tables. So these are what I said before. And code and flag tables are numerical values to be encoded where the element values are qualitative. So code and flag tables are, of course, also a part of buffer tables. So the first table A is actually defines the general category of the data contained in the buffer message, and this is referred in buffer section 1. So these are the examples of typical entries. So if the code figure is 0, this means surface data. And if the code figure is 1, this is surface data in the sea, on the sea, or something like that. So if you need to know the data category, you need to refer table A and these code figures. And table B is this. Table B describes the individual values that are encoded, and element descriptors are grouped according to classes. So these are the examples, and the class number 0, 02 is like represent identification or instrumentation and everything. So probably next one will be, So the next, this is the excerpt from the class 01 identification class descriptors. So these ones are table B descriptors, which is element descriptors. So as I said before, the descriptor is described, represented using f, x, y, 1, 2, 3 digits respectively. So now the class 0, 1 actually represented in x. So these are, sorry, this example x is 0, 1. So this means class 0, 1, and which is identification. So probably you will see a lot of times the descriptor 0, 0, 1, 0, 0, 1, which means WMO block number, and 0, 0, 1, 0, 0, 2 is WMO station number. So this, using these using these two descriptors, you will have the WMO station number. So this is another excerpt from class 11. So 11 actually represent wind and turbulence. So in class 11, we have these descriptors. Probably this is excerpt, so not all, but some examples are wind direction, wind speed, and everything. So if you read 0, 0, 1, 1, 0, 0, 1 in section 11, you will expect you will have wind direction in the corresponding location in section 4, data section. That's how it works. So as we saw in the examples, table D have columns representing table reference, element name, unit scale reference value, and data width in bits. This is a little bit confusing part of buffer, but so scale reference value and bit width are chosen so that the desired range of possible data values can be stored in buffer as positive integers. Yes, so it's hard to. So this is a bit repetitive, but table B reference is expressed as 3 small numbers f, x, y, used to refer to this descriptor. F is always 0 for one element descriptor. X is in the range of 0 to 63 and refers to a broad class of elements. So classes 48 to 63 are reserved for local use. Y is in the range of 0 to 255 and reference to the individual descriptor in the class. Within all classes, descriptors 192 to 255 are reserved for local use also. So the table D element name is a natural language description of the meaning of the value, usually English, but could be translated to other languages as well. So the examples are like brightness, temperature, or total precipitation past 3 hours, or wind speed at 10 meters. So it's a very intuitive thing. So table B also has a unit, of course, which this physical element, physical quantity is represented in which unit. Of course, we need that. So the unit used for the value, normally SI units are used. The international version of ASCII is used for character data, such as identifiers. And call table is used for qualitative data, where only one of a set of possible values can be applicable in a given data subset. Flag table is used for qualitative data, where more than one of a set of possible values may be applicable in a given data subset. So for qualitative data, the coded values are references to the code and flag tables. Probably you will see well in the example. So Also, table B has a scale, and scale is a power of 10 by which to multiply the data value before packing. So determines the precision with which the data are encoded. So a scale of 2 means 2 decimal places of precision. So for example, 273.16. So the scale of 2 means 2 decimal places. Yes. So this is something related to precision of the data. If a scale of -1 means that the data values are rounded to the nearest multiple of 10. So the reference, the another thing is reference value. This is used to subtract an offset where a negative data have to be encoded. So table B contains the value multiplied by the scale of the offset to be subtracted. So for example, scale equal to reference value -9,000 means that, so as I said before, scale 2 means the 2 decimal here. So that -1900 is to be subtracted before scaling. So allowing value as negative as 19.00 to be represented. Probably you need a little bit need a calculation, but you'd understand. Yes. So the table B entries also have a data width. So data width is the number of bits to be used to encode the value. So if all bits are set to ones when encoding, then this denotes a missing value. So all ones are missing. This is a kind of unified definition. So if the scale is S, the reference value is R, and the data width N is N, then the representative range of value is minimum to maximum. And this denotes the missing value. This is probably, you will understand with some after some calculation. Yes. So let me give some example. So the 0,11012 actually is a wind speed at 10 meter. So scale is 1 here. Scale and reference value and data width I'm talking about. So precision is 1 decimal place, represented by scale equal 1. So it's now, which is 0.1 meter per second. The minimum representative value is 0. Maximum representable value is 409.4 meters, and missing is this. So you need to understand. Decoder take the scale reference value and data width, and decoder will know missing value is here. So this number actually doesn't represent wind speed, but means missing. So depending on descriptors, missing value are different. That is a really confusing part. But in many cases, I have some buffer from the data buffer. Well, wind speed can't go 400, for example, so it's not that complicated, as you understand first. Okay, this is the same, but I'll skip it now. Yes, this is also the same. Yes. This is an example of code table. So if a descriptor has a code table, of course there is a code table corresponding to that descriptor. And for example, 020003 is a present weather. It's a complicated one, but so there is a code table named 020, 003, and you see these code figures. So if the data has number 0, then this means cloud development not observed or not observable, something like that. So each code figure has its meaning, and you will know the meaning from the code table. Flag table is similar to this, but it's a little bit different. So take me. What to say? So flag table, each bit has separate meaning. So you can have multiple ones and zeros depending on each bit meaning. So if surface vertical, the one example is vertical sounding significance, and you can choose 0 or 1 for each bit. So it's 8 bits. So flag table is a bit different, but 0 or 1, you can choose 2 of them. Sorry, this is a little bit complicated, so I'll skip it now. Table C has table C is descriptors or operators, and we can manipulate this meaning of descriptors using these various operators, but we also skip it because of time constraints. So you can refer to the manual codes always. Yes. So time-wise, okay. So table D is another important table, and table D describes sequences of descriptors, and columns are it's also represented by 3 parts, f, x, y, and f is 3 for table D. So if you have a descriptor starting with 3, then you will know these descriptors, that descriptor is defined in table D. So you go find this one in table D. This part is totally the same as table B descriptor. So x is range of 0 to 63, and the range of 48 to 63 are reserved for local use, and y is the range of 0 to 255, and entries from 192 to 255 are reserved for local use. Table references, list of other descriptors including element descriptors, table B, replication descriptors, operator descriptors defined in table C, and other sequence descriptors, table D is referred. So which means table D descriptors include other types of descriptors. So this is kind of layer structure. You will see the example. So just like table B entries, table D also have categories. So categories examples are here. So if the category means the X part, 2-digit X part, if category number is 01, this would be location and identification sequence. And if category number is 2, that sequence is common to surface data. So this kind of classification of table D descriptors. So here comes the example. And this is the category 01, which is location and identification sequences. And yeah, I showed the 2 examples of table B descriptors of 001001 and 001002. And these two constructs, or combining these two table B descriptors makes one table D descriptor. So sorry, if you see 301001, then you can translate this descriptor into these two descriptors. So this is the simplest example of table D descriptor. So by using 301001 instead of two descriptors, you can describe WMO station identification with only one descriptor instead of two. Maybe another basic example is year, month, date. So these three table B descriptors, which is element descriptors, creates 1301011 table D descriptors. So using 301011, you can describe year, month, day with only one descriptor. So having these three descriptors and having one this descriptor means totally the same. But by using table D descriptor, you can have a shorter descriptor section. So it's 1/3, for example. And the table, this is a very simple example, but table D descriptor can be very long. So like set of, for example, 70 table B descriptors can be represented with only one. So this is the point. So the last one is kind of one of the template examples. And if you see 301038, you can translate this into these 6 descriptors. And as I said before, table D descriptor can include, again, table D descriptor. So this is kind of layer. So you'll see 301001 here. So once again, you need to go back here, and you would know table 2 element descriptors. So this is some kind of template of run station for vertical soundings, and this consists with WMO block and station number and radio zone type, radio zone computational method, and date time and location. This is another BUI platform fixed template. So you can again go C301033 it's called template for BUI. And how you can know the descriptors? You can go first table D and look for this set of descriptors. And if you have another table D descriptors in the template, you can go back to the definition of 301011, for example. Yeah, so I keep using a word of BUFR template. And maybe it's a little bit confusing first, but BUFR template is a table D descriptor, which is a common sequence. It's also called common sequence, to describe a data set distributed as an independent report, typically a combination of multiple descriptors and common sequences, representing station, time, and location information, observation instrument information, physical quantities. So the template is a word used for common sequence that are independent reports, such as sign-off, shift, temp, climate, everything. So, but the other common sequences that are not reported as an independent report are not called as templates. So, for example, WMO station index, this is an example I showed before. It's 301001. Consists of two element descriptors. But this is also a table D descriptor and a common sequence, but this is not called a template because WMO station index is not reported as an independent message. So this is a good to know template and common sequence, the difference between common sequence and template. Maybe we can. So the example BUFR templates are like 307080. So this part is actually a table D entry, and this is a kind of convention that TM and table D numbers is sometimes used for representing a template. So in the TM307080 is actually a BUFR template for sign-off. So consists of looks like this. So set of other common sequences and element descriptors. So BUFR templates has been developed along with the regulations to convert TAC. So now these templates are included in manual codes as a BC regulations. That's also good to know for converting purposes. So I think I come to the next, the last one. So, okay, BUFR is flexible, as I said in the second day presentation. So it can represent a wide range of data types. The BUFR is table driven, as we saw. Tables A, B, C, and D, and code and flag tables contain majority of information needed to encode and decode data. So BUFR is self-describing. The data description section describes the data using element, table D, replication operator, table C, and sequence, table D descriptors. I skipped a little, but replication descriptors and sequence descriptors can be used to reduce the size of the data description. And also compression can be used to reduce the size of data themselves. I think this is all. I included all the resources here, so you can always refer to publication, manual codes, and other BC regulations. And if you have any questions, you can always contact me, please. Yes. This is all. David, thank you. Yes. Yes. The advantage. Yes, yes. Yes.
We'll give you an example just to then questioning about. I have a decoding program.
Mm-hmm.
Say it is 2020. Let's say.
Yeah.
Is it going to be able to decode a buffer message reduced to 2015?
2000. Sorry, reduced.
I have program, decoding the program for buffer.
Yes.
Reduced to 2015.
Reduced, produced.
Let's say an example.
Yeah. Yeah.
Is it going to be able to decode or encode a buffer message reduced to 2015?
You
It's
need to.
self-describing.
You
It is
yeah.
carrying in its own package the keys to decode or encode the message.
You need to update only tables. you don't need to change decoder software itself, but you need to have a new table version.
Update just the table.
Tables, yes, yes,
Table is removed or cancelled or changed or modified.
yes,
That's okay. But
yes.
same
Same
software
decoder can be used. Yes, that's the thing. So that's flexible and scalable. So only tables change, but software doesn't change. So maybe we deserve a tea or coffee after this.
We should continue to talk now.
Yes. Is that the complete presentation or is there anything else?
This is a summary and resource and contact person. Yes.
So
And
that means we're finished.
another one, the planning thing, but it will be shorter, like 30 minutes.
All right. So let's have tea or coffee now, and
Yes.
let's take maybe 20 minutes
Yes.
for the last presentation.